So, what have we got here? We've got a first of our problems with centrifugal and centripetal force. So we've got a girl, mass 25 kilos, she's sitting on a roundabout or a merry-go-round or whatever you want to call it. And she has got her centre of mass, so where she's sitting, the centre of mass is 1.5 meters, so that's our rho. This rho is this radius of the motion, and it's going to be to her centre of gravity. So the rotation of the roundabouts increase slowly so that the girl does not slip tangentially. So why are they telling us that? So they're basically telling us that, so she's gonna, in order, if suppose you increase, this guy pushes this really hard, then there'll be a tendency for the girl to slip tangentially, which would be in this direction. So she'd tend to slip back that, oh, well, it depends which way he's pushing her. So he's pushing this way, so she'd tend to slip back this way if you increase that rotation really quickly. But usually in these questions, we're not really going to be looking at that for this course anyway. We're just looking at the force in the radial direction. So they're just saying the guy increases the rotational speed of that roundabout slowly. And so this would be the tangential acceleration or velocity would be in this direction or this direction. The radial acceleration would be this way or this way. Radial forces would be that way. We're going to be interested in those ones, so probably easier just to think about if she was a section through the roundabout, that's her sitting on the edge there, and then we could draw a free body diagram of what's going on here. So what have we got? We're going to have a centrifugal force which arises because of the inertia of that girl. And so when you're changing direction, so this one, it's not changing speed, just changing her direction, you're going to get a centrifugal force like so. What we call that, we'll call that FCF, for example. And if she is going to be rotated, there must be some kind of centripetal force, so centripetal reaction in the other direction. Now we're just going to ignore, I think in this question, we're just ignoring the moments we're assuming that she's going to manage to balance herself. She's got the hands down here. She might lean back a bit or something like that. But the reaction to that centrifugal force is going to come because of friction. And so if everything stays in equilibrium, we're going to have a friction that's going to be equal and opposite to the force that arises because of her spinning, the centrifugal force. And this is the centripetal force. But we're just going to call it, it's a frictional force, so we'll just call it F, as usual for a frictional force. What else have we got going on? We have got, again, I'm just doing my primary forces. So it's almost like a statics problem, but the reason it's not a statics problem, this is an inertial force. It only arises because of the acceleration of this girl. So the girl's accelerating. And so it's not really a statics problem. But if you draw on these inertial forces, we'll still find everything balances out. But another force we've got her weight. Let me just actually draw it like so. So we've got her weight. Nothing's to scale in this. Just check I've got the right zoom. Yep. And then to counteract that, to balance that, and she is in static equilibrium in the vertical direction. She's not accelerating up or down. She's just staying at the same position vertically. And so in that direction, we do kind of have static equilibrium. But the reaction to that is here, and it's going to be a norm. So that's our normal force N. Okay, so we're kind of bringing in the frictional stuff into this as well. Now, that centrifugal force, that's horizontal. So it's a radial force, so it acts outwards from the direction of, or from the axis of rotation. So you've got your axis of rotation here, the center of rotation's here, and so that centrifugal force is acting out the way, that force that arises because of the mass of this girl being accelerated to make a circle, not changing her speed, just changing the direction of the velocity, but that still has to have an acceleration associated with it. So it creates this force. So we've got a centrifugal force outwards that's balanced by the frictional force acting towards the center of the roundabout. Both of those are radial forces. And we've got a vertical force from her weight and a normal reaction to that. And the normal reaction is just equal to the weight because this centrifugal force doesn't have a vertical component. So what do we have to do? We've got to figure out what the maximum speed she can have before she begins to slip. So we're thinking back to the friction and the graphs for friction. Just do a quick sketch of that. And so if you remember, if we plot applied force in one direction, or so that would be our friction in that direction, applied force in this direction. So this would be P, this would be F. We've got some kind of little block like so, and we're pushing it with a force P, and we've got a resisting friction F. What happens to that? Well, it increases, and they're equal to each other, so you get static equilibrium until it gets to Fs, the static friction. Then it drops, and then it would slide after that, and it would have a slightly lower friction, Fk, so the kinetic friction. If you're thinking in terms of displacements, you would get something like, I'm sorry, I'm not using a ruler, it's a bit sloppy, but anyway, so you're going to have a force P, sorry, this is displacement. Call it whatever we want, let's call it S. And suppose this was the applied force. So your applied force, let me just do it in blue so you can see it. So the applied force would increase until it got to Fs. And then if you kept displacing this thing, the force you'd have to apply to keep moving it would drop down, and that would be Fk. Fs, Fk. So just keep that in your mind. So what we're interested in here is when she starts to slip, so it's this value of Fs is what we're interested in, and they should have given us the static coefficient of friction. It's 0.3. So let's just start writing down some of the things we know. We know that the F, we can call that whatever we want, FCF, the centrifugal force, is equal to mass times velocity, well, speed squared, mass times speed squared, divided by the radius of rotation, so divided by rho. And does it give us her weight? It might not. It does. Well, let's just stick that in. So it's going to be 25 times speed squared, and I'm just putting those bars around the speed, so these vertical bars, it's just showing that's the magnitude of the velocity, which is speed. That's the only reason you put those there. So v squared over 1.5. 25 divided by 1.5, it's not going to give us a particularly nice answer, I don't think. Just a second, I'm just going to pause while I find my calculator. So that's going to work out as 1.67 v squared, sorry, 16.67 v squared, 16.67 v squared is what the centrifugal force is. The middle balanced by the centripetal force, and the centripetal force is coming from friction. Now we know that the value of the friction, that's our other equation. Oops, I don't know what happened there. So friction is just equal to, or the static friction, the point, or the static force of friction, point at which she would start to slip, the point of impending motion is another way to say it, is the coefficient of static friction times the normal force. We should have probably figured that out first. Let's bring that down here. So if I was, well, let's just keep writing. So we know that the normal force is equal to her mass times gravity, which is 25 times 9.81, which is equal to 25 times 9.81, 25 times 9.81, 245.2-ish newtons. So therefore, and we also know mu_s is equal to 3, so the static coefficient of friction is 0.3, 0.3 times normal force is 245.2 newtons, which is equal to 73.58, say, 73.58 newtons. So what will happen is he'll increase this this fellow is going to increase this rotational speed slowly, so she's not going to slip sideways or tangentially, she's not going to slip that way, and he keeps increasing it slowly. The point at which she slips is when this centrifugal force, which is getting balanced by the friction, it can only increase as far as the static frictional force, so the maximum value of this Fs, and once it goes above that, she'll start to slip off this roundabout. So we want to find, for that point of impending motion, we just want to find the point at which those two things are equal. So let's say for impending motion, or we could put it more, what's the word more practically? For point starts to slip. Then the centrifugal force is going to be equal to the maximum friction, which is the static friction, which is going to be equal to, so therefore we're going to have 16.67 times speed squared is going to be equal to 73.58. Therefore, speed squared is going to be equal to 73.58 divided by 16.67, which is going to be 4.414. Not get to units yet. Then we need to take the square root of that. So it's going to be the speed. Take the square root, could be plus or minus. But then it's speed, so it can really only be plus. So let's get rid of that. But what that does kind of indicate is it doesn't matter whether this fella pushes it this way, or he could push it that way, rotate it that way, it wouldn't make any difference. So you'd still get her slipping in either direction. That's kind of what the plus and minus is telling you. But anyway, we're talking about speed, in which case neither here nor there. 2.1009 is what I'm getting. So 2.10 meters per second. So girl will start to slip when her speed equals 2.10 meters per second. Seems pretty fast. If we just think about how many rotations that would be, so for her to go around once, one revolution is going to be the distance for one revolution, is equal to pi times the diameter, which is just going to be pi times 3, because it was a 1.5 radius. And so would that be, it's quite a lot. So it's, where's my pi on this calculator? Pi times 3 is equal to, so that's 9.42 meters. 42 meters. So she would have to go, say about 10, that's about 2. So it's going to take 5 seconds for one revolution. That seems reasonable. You could imagine that. You could do that with a roundabout. And so it seems pretty reasonable. So that's our answer. Now, just 1 second. Oh, easy way to check this. What I can do is just chuck that back into this equation. So we're going to have 25 times 2.1 squared divided by 1.5, 73.5-ish. And so, yeah, we're getting about the right 1.3 times 245.2. It all seems reasonable. The only real way to check this is just to go through the calculations again, really. But that's it. Okay, let's move on to another one.